Tianxie, and I'm excited to present our work titled Deep Active Learning in the Open World. I will guide you through our approach to active learning in dynamic open world environments. Let's begin with the motivation behind our research. Machine learning models have made remarkable progress, but most of them assume a closed world scenario where training and testing data come from the same distribution. However, in real-world applications, models often encounter new, previously unseen classes, as seen in the figure. In a dataset with fish, chicken, dogs, and elephants. Initially, only samples of fish and chicken are labeled. The dog and elephant samples belong to unknown classes. These out-of-distribution data points can severely impact performance. Handling this issue efficiently is essential for the development of open-world learning systems. The key challenge is how to allow a module to discover and learn new classes while keeping the annotation costs low. Moving on to the challenges, as mentioned in our motivation, most active learning research is set in a closed world. Moreover, relevant research and methods are usually tailored for specific tasks. This limits their effectiveness when facing more general problems, like image classification. When developing our method, another issue we face is that we can rely solely on traditional uncertainty measures like high OD, out-of-distribution scores, can lead the model to focus on only a few unknown classes. This is because the highest scoring examples might come from a narrow subset of data, causing the annotated set to be unrepresentative of the full diversity in the unlabeled pool. This brings us to our main contribution, ALLOY, which stands for Active Learning in Open World Environments. ALLOY is designed as a two-stage approach. In the first stage, we use diversity sampling to select a representative set of examples. More exactly, we applied k-means clustering methods to the embedded features of unlabeled samples, while making sure the number of clusters are larger than the budget size of each iteration. After getting the clusters, we move to the next stage. In the second stage, we employ an out-of-distribution detection strategy using grand norm scores. By calculating these scores, we are able to calculate the proportion of predicted out-of-distribution examples within each cluster. The top clusters with the highest proportion are selected, and from each cluster, the sample with the highest OD score is chosen for annotation. To evaluate our approach, we conducted experiments on several long-tailed image classification benchmarks, including CIFAR 100, ImageNet, and Places 365. These datasets are characterized by highly imbalanced distributions, conditions that closely mimic real-world scenarios where some classes are underrepresented. In our experimental setup, we began with a very limited set of labeled classes, sometimes as few as 3, and allowed the algorithm to actively expand this set. The model we used was based on a fine-tuned CLIP model with a linear classification head, and we iteratively restrained the model as more data was annotated. This iterative process is crucial because it mirrors the way models learn in a dynamic, open-world environment. Now let's talk about the results. Our experiments demonstrated that ALLOY consistently outperforms traditional active learning baselines. For instance, on the ImageNet dataset, in the early stage, our approach was able to save up to 70% of annotation cost to achieve the same level of accuracy compared to random sampling. And in the long-tailed versions of CIFAR 100 and Places, our algorithm also performed best among all algorithms. An interesting observation is that while Alloy excels at rapidly discovering new classes, there is a trade-off. When most classes have been discovered, some baselines might catch up or even slightly outperforms Alloy on known classes. This indicates that while discovering new classes is critical, there is also a need to ensure robust learning of the known classes, a challenge that remains open for future work. In discussing our results, it is important to acknowledge this trade-off between new classes discovery and learning of known classes. Our experiments suggest that there is a balancing act. We want to explore and discover as many new classes as possible, but we also need to refine the module's performance on these classes that are already known. This observation opens the door to potential adaptive strategies where the focus dynamically shifts between exploration and consolidation as more classes are discovered. For future research, one promising direction is to develop adaptive algorithms that can adjust this balance dynamically. This idea would be to initially prioritize discovery when the module has limited knowledge, and later shift to a consolidation phase once most of the classes are identified. To conclude, our work on Alloy represents an important step toward active learning in open world scenarios. By combining diversity sampling with out of distribution detection, Alloy is able to efficiently expand the module's understanding in environments where unknown classes are prevalent. Although challenges remain, especially the balance between new classes discovery and known class learning, we believe that this work lays the groundwork for future advances in adaptive, label-efficient learning systems. Thank you for your attention and time.